Hello, Professor Gauri Shankar. Am I audible?
Yes, sir. Yes.
Good afternoon. So,
Good
shall we start?
afternoon.
Yeah,
Yes, sir. I think we should.
yeah. Okay, so good afternoon, all. Let me share my slides with you. Is the screen visible?
Yes, it is.
Yeah, thank you. Okay. So, yesterday we were defining the orientation, induced orientation on a boundary of an oriented manifold. Okay, so the fact that I was trying to get at by drawing pictures, I'm going to state that fact, and I will invite you to come up with proofs. Okay, so for a manifold M with boundary dm, there is an outward pointing continuous vector field which we will denote by capital N. Okay, so this is something that one needs to establish first. If you have a manifold of dimension n, then at any interior point of M, the tangent space of M, TPM, has dimension n. But then the question is, what if we choose a point on the boundary of this manifold? What is then, if you are on the, let's say, boundary, so this is your M, and if you take a boundary point, what should be the tangent space of M at the boundary point? So once we resolve this question, then the existence of outward pointing continuous vector field is solved. Okay. So the definitions of tangent vectors that you have come across, you can take up any of the definition and try to show that the dimension of TPM whenever P belongs to the boundary is also equal to N. Okay, so I have a full tangent space at boundary points also for M. Okay, one heuristic reason is that if you have a path, if you think of tangent vectors as equivalence classes of smooth paths, then you can have paths that end at this boundary point. Okay, and when you locally take it to the standard model of upper half space, you can slightly extend this path. Is there any question? Okay, looks like there is. Yeah, if you are commenting, I won't be able to see the comments because while I write, my screen just shows me the thing that you see. So please interrupt by means of voice so that I can relate to your questions and comments. Okay, so right. So the tangent space at boundary points is has dimension n, and here there is certain sense of inward and outward, because if you have a path that is approaching the boundary point, its tangent vector at the point P is going to point outward because path is going towards the boundary. If the path is going away from the boundary, then it will give rise to a tangent vector that is pointing inward. Okay, so maybe I can draw this picture a little bigger. So this is your point P, and I'm looking at vector that is pointing outward. So this is just M. M is on this side, and you may have a path that approaches this point, and this is like the tangent vector at this point. If imagine if you had extended this path locally when you had taken this half chart, which maps diffeomorphically a region around a small neighborhood around this point P to a small neighborhood of, let's say, origin in upper half space. right? So one can extend uh, these things and make sense of tangent vectors which are pointing outward and inward. Now, once you have existence of locally defined outward outward pointing continuous vector field, you can simply take this from upper half space and map it onto the manifold. So again, we can play the same game. If you have another chart, you extend this vector field across the boundary. Okay, so you do have a outward pointing continuous vector field, which is implicitly uh, we are saying that it is non-zero, because in order to have an outward pointing vector field, you have to have a non-zero vector field. So we are going to denote it by n, and the induced orientation on the boundary of M is going to be as follows. So how do we orient the tangent spaces of the boundary? Pointwise. Okay. So so that the orientation of M is used while orienting the boundary. So for that, you start with an ordered basis of TP dm. So this is tangent space of the boundary. We say that it is positively oriented with respect to the orientation on the manifold if now you plug in the first vector as the outward pointing continuous vector field n, and then follow it up with this ordered basis that you are given. Then you get n ordered basis for TPM. So if this ordered basis, n comma v1 comma v2 up to vn minus 1, if this is positively oriented basis of TPM with respect to the orientation, then you say that this v1 v2 up to vn minus 1 is an is a positively oriented basis for the tangent space of the boundary. Okay, now you at every point you have positively oriented ordered basis, and you can see that because this vector field n is continuous, you can show that all these you have a continuous choice of positively oriented basis on the entire boundary, and therefore boundary gets induced orientation from M. So let us see how we were trying to relate this in the case of annulus yesterday. We geometrically saw this, uh, but now we will make use of this definition and arrive at the same conclusion. So this is the annulus A. It has two boundary components, the outward boundary and the inward boundary. So now the red arrow is denoting an outward pointing vector at this point P. So I have to take a tangent vector, non-zero tangent vector to the outward boundary in such a way that I will get an oriented basis of the annulus, the tangent space of annulus at that point. But recall that the orientation on the tangent spaces of the annulus is given in the counterclockwise fashion, right? So therefore, you see that here, if I take n in the first slot and this green vector that I have drawn in the second slot, then my convention is followed. I go in the counterclockwise fashion. Okay. So at any point on the outward boundary, my induced orientation would be in the counterclockwise direction. Now, let us see what happens at the inward boundary component, at the interior boundary component of the annulus. So this you see that the outward pointing normal of the outward pointing vector is shown by the red arrow, and you have to take a tangent vector so that this red arrow and the green tangent vector form an oriented basis of the annulus. So which means that you have to go in the counterclockwise direction and get this vector. So you see that as a result, the inner boundary component of the annulus receives clockwise orientation, which is what we saw yesterday using geometric argument, right? Okay, so now you imagine that this thing happens for an abstract manifold. In this example, it was easy to think about this outward pointing vector field, because I am looking at, when I am drawing this picture of annulus, it's a planar diagram, so it's an embedded submanifold of R2, and therefore it is easy to imagine this outward pointing and inward pointing vectors at the boundary points. But for an abstract manifold, the outward pointing vector and inward pointing vectors do make sense. Okay? And that is what we started with. So now we are ready to define the notion of integration on manifolds. Okay. So let me pause before I go into integration on manifolds. Let me invite if there are questions, comments, suggestions till this point.
Hello.
Yes.
Sir, if n changes its position, suppose it is v1,
Yes.
v2, vn minus 1, comma n,
Yes.
then does the orientation reverse?
It may reverse, it may not reverse. In this case, it will. For
It will.
two-dimensional case, it will.
Okay.
Okay. In fact, if you change the sign of n, then also orientation will reverse. So let me,
Yes, sir.
for example, the orientation class of n comma v1. Let's say in two-dimensional case only, n comma v. This is not so. This is different from minus n comma v. Okay. So you just you see this happening, right? So let's say in planar case, if you have the vector n and the vector v in this way, so that they follow this counterclockwise rule. Now you take n pointing in the opposite direction, that is minus n. So this is minus n and this is v, and then you see that you have to go in the clockwise direction. Right? So orientation reverses if you put a minus sign in front of precisely one uh, vector in that ordered tuple. Okay. Now,
Thank you, sir.
yeah. So and also the change, we can have this convention. So let us say that this symbol is it can be said that this is equal to minus of s minus n comma v. So because orientation is either positive or negative, we can put this minus sign in front of the bracket. Okay, and same thing we can show that n comma v is the negative of orientation v comma n. Yeah, yeah, that was a good question. Yeah, if we uh, change the position of this vector n, then there will be a change in sign. But how do you find out what is precisely the change in the sign? So, for example, n here appears uh, in the third spot instead of first spot. Then, to achieve this thing, you need two transpositions, right? So, you look at the sign of corresponding permutation and put that sign in front of the orientation class. That is the orientation class you are looking at after permuting this ordered basis. Okay. Yeah. Is there any other question on orientations? Okay.
Yeah,
Is there
there
any
is one comment.
Yes, yes, please go ahead.
I commented just insight of René Thom
Huh.
on just these ideas.
Huh.
With this concluded that the real projective plane,
Hmm.
which is a compact two-dimensional manifold, cannot be a boundary of a three-dimensional
Oh,
manifold.
yes. Yeah, that's a nice comment. Yes. Yes,
And
because
that,
all three dimension. Yes. Yes. So let me elaborate on that comment of Professor Kulkarni. It's a very interesting comment at this point of time. So what he said that this cannot be boundary of a three manifold. Okay. So the reason is every yeah. Please go ahead, sir. If you are saying something, I'm sorry if I cut you short.
no, okay, go. Yeah,
Huh.
right.
So here the manifold M is a compact manifold, compact three manifold. So the one can show that any compact three manifold is parallelizable. So which means that the tangent bundle is diffeomorphic to or bundle isomorphic to M cross R3. Okay. So you can give an orientation because you have a global frame available, right? You can take a frame and declare that this is the frame that is giving you orientation. So from what we have seen so far, it means that if M has a boundary, then it would get an induced orientation, and therefore if RP2 was boundary of some compact three manifold, then it would be oriented. But yesterday we saw that the Mobius band was not oriented, and you can show that RP2 is union of Mobius band, let's say Mobius band, union a disk. Okay, you can do this union, take this union along their common boundary in a smooth fashion as well. Okay, and because RP2 contains the Mobius band, you can show that RP2 cannot be oriented. Yeah, yeah. So thank you. That was a very interesting remark at this point. Yeah. So okay, I will now move on to integration on manifolds. So idea of integrating functions on Euclidean spaces. If we try to mimic that idea on the manifold, obviously we will first try to mimic that idea locally and then somehow show that when you do coordinate change transformation, whatever notion we define of integrals should be independent of the change of coordinates. Then we would get a global notion of integration. So if we just try to mimic the idea uh, of integrating functions on domains in Euclidean spaces, that does not go through. The reason is function as it is need not be independent under the change of coordinates. You can construct functions. For example, if I have a compactly supported function just within a chart, and then I try to mimic this idea, then you see that the coordinate change does not keep the function invariant, because if as soon as you enter other chart, the function may be zero, who knows, right? So therefore we have to think about, instead of functions, we look at integrating n forms. Okay, the reason is the suggestion comes from the change of variable formula that we have seen in our first lecture. Okay, and at that point, Professor Kulkarni was also pointing out why take absolute value of the determinant of the absolute value of the Jacobian. Why not just take Jacobian? The reason is we have been just focused on uh, orientation preserving maps in order to do change of variables for computational purposes. But at that time, we had completely ignored this aspect of orientation. Okay, so with that in mind, we can see that if we take the volume element as it is, and uh, we take the function f times the volume element as our n form, and think of the integration of a function as integration of the n form, because function times the volume element is an n form on Euclidean space, right? So we are going to make that idea precise, and we will see, because of the change of variable formula together with this idea of orientation, we will be able to show that such integrals are independent of change of coordinates. Okay, so that will be my goal for coming 20-30 minutes. Okay, so yeah, so what we will first try to rewrite integration of functions on domains in Rn as integration of n forms, okay, on Rn. So we'll first set up the local case. So let d bar be a smoothly bounded domain, which means that d bar is the interior of d bar is an open set within Rn. We may take it to be connected, though it is not connected. Disconnected issue is irrelevant in this discussion. Let us take this to be a ball, for instance, together with its boundary. Okay, and let's assume that we have an n form. Our original idea is we wanted to integrate the function f on this domain. Uh, so instead of that, we will look at the n form given by f times dx1 wedge dx2 wedge dxn. Okay, so you have the volume form, a preferred volume form, because you are working in Rn. So you have the global coordinate system x1, x2, xn. So I take the volume form given by their wedge product. Now this f, we will assume for a moment that it's a smooth function, though all the analytical issues, if we try to reduce the regularity, we will not concern ourselves here with those issues. So we will define the integral of omega on this domain D. Okay, so let me say that this d bar, though it is not going to make a difference, but so we define the integral of omega on this domain d bar to be the integral of this f times the volume form or the volume element. Okay, and in practice, how do we compute this integral? It is simply, you simply forget the wedges and you get your familiar notation dx1 dx2 wedge dxn, and we know how to integrate then function. Okay, in the usual case of Euclidean higher multiple integrals. Okay, so we know that the right hand side is a familiar object and it gives out a real number, and that real number you define as the integral of omega over d bar. So now before we move on and generalize this definition onto manifolds, this is going to be our local definition. We need a small concept of orientation preserving or orientation reversing diffeomorphisms. Okay, so let m comma o and n comma o prime be two oriented manifolds. Suppose f is a diffeomorphism f is a diffeomorphism from M to N, we say that f is orientation preserving if the derivative of f at every point takes a positively oriented basis of TPM to a positively oriented basis of TFPM. So at every point, the isomorphism given by DFP should be an orientation preserving isomorphism of vector spaces. So that tells you the determinant of equivalently the if you express the determinant of this linear transformation DFP, that should be positive with respect to the orientations that we have chosen. Okay, so let me say equivalently determinant or the Jacobian in this Jacobian of f at p should be positive for all p. So now we are ready to put a version. Let us state a small lemma or an observation that
Sir,
yes, go ahead.
you mean the Jacobian of DF, right?
Yes, yes,
Uh,
yeah, right. I meant Jacobian. Well, Jacobian is a derivative of it's a matrix of partial derivatives of f. So
okay, so
uh,
that is why it's written Jacobian of
uh,
F.
yes, yes, right. So we will now extend this change of variable formula, taking into account the notion of orientation. Okay, so let us see what we get. So if U and V are smoothly bounded domains in Rn, and F from U closure to V closure is an orientation preserving diffeomorphism from U to V. I meant U bar to V bar. So when I say, when I assume that F is a diffeomorphism, it means that the boundary of U will go to boundary of V. It is implied in the assumption. Okay. So, and if you don't see it, it's a good exercise to solve, to see that why diffeomorphism from U bar to V bar will take a boundary point to a boundary point. Okay. So now if omega is an n form on V, then the integral of pullback of that form via f on U is same as integral of omega on V. Okay, so this you get for orientation preserving case. But what if you have orientation reversing case? Okay, so what if f was orientation reversing? Then in that case, you get minus of integral of omega on V. Okay, so let us quickly see why this is true. So let us assume that y1, y2, yn are coordinates on the domain V, and x1, x2, xn are coordinates on U. We will write this omega in, as smooth function times the volume form given by this coordinate system, which is dy1 is dy2 dot 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 is dyn. Now the change of variable formula we will imply the following thing. So if I integrate this omega on V, then by definition that we just introduced, we will integrate f with respect to the volume form in this coordinate system. Right? Now you apply the change of coordinate formula as we stated. We know that this y1, y2, yn is we could have we can take this coordinate system x1, x2, xn as coming out of f. You shift this y1, y2, yn via f to a coordinate system u on the domain. Sorry, coordinate system on the domain u. Then the change of coordinate formula tells you that you have a factor which is absolute value of the determinant of Jacobian determinant of so let me say JF times the volume element. But if we see what this quantity is, Jacobian is, we know that this can be rewritten as determinant of df, obviously at point P. This is happening point-wise, so we are not referring to the point. Okay, so and the other side is the volume form in the coordinates x1, x2 up to xn. This is the case because determinant df is going to be positive. The reason is f is orientation preserving. We just defined the orientation preserving diffeomorphisms. So therefore, if we now look at this side, what we see is that this is just the integral of the pullback form omega on u by definition of pullback of forms. Okay, in case of orientation reversing, we have that determinant of df, I meant, so df is negative at all points, and therefore if I want to take the absolute value of determinant of f, I will take minus of df. And now if you do this thing with the minus of the determinant, you will pick up a minus sign. Okay. So whenever you have a change of coordinates that is orientation preserving, we know that the change of coordinate formula is just telling us that the integral of an n form on domain V is same as integral of the pullback form on domain U. Okay, so now this is going to help us in setting up the integral, the notion of integration on manifolds. Okay, so let me pause and see if there are comments, questions, suggestions here at this stage. And I'll also have a sip of water. Okay, so looks like this is all right. So let us move on to now generalizing the local idea of integrals of n forms to the integrals of n forms on manifolds. Okay, so again we will do it step by step. First of all, let us assume that M is an oriented manifold with of dimension n, and the orientation is denoted by O. So let omega be an n form, smooth n form on M. We will first assume that omega is compactly supported, and in particular we will assume that the support of omega lies within a single chart. Okay, so when support of omega lies within this chart u comma phi, we will define integration of omega on M to be, so now it is equal to plus the integral of pullback form via phi inverse map of omega over the domain phi of u. This is the case when you are considering a positively oriented chart. Okay, so if the chart is positively oriented, this means that phi becomes an orientation preserving diffeomorphism from U to an open subset phi U of Rn, and on Rn there is the standard orientation given by the global frame E1, E2, En, right? So that is why we put a plus sign, and this is equal to the minus of the same integral if u comma phi is negatively oriented. Okay. So this is our definition, but in the definition, if you look at the notion that we are defining integral of omega on m, and we are making use of the chart. So we have to check something here. We have to check that this definition is independent of choice of this u comma phi. It may happen that support of omega is contained in another chart, let's say u tilde phi tilde. Then we will have to check that the integrals that we have defined are independent of the choice of the chart that we are using. Okay, so let us quickly see why this integral does not depend on the choice of coordinate chart. So case one is that you have these two charts, both of them containing support of omega. Now, first case is that let us assume that both charts are positively oriented or negatively oriented with respect to the orientation class O on the manifold M. In either case, the determinant of the Jacobian of the coordinate. Okay, again I get. Okay, so the determinant of the coordinate transformation that changes the coordinates from u tilde to u. If you look at determinant of the derivative of these maps at any point, they will be positive because we are assuming either both of them are positively oriented or both of them are negatively oriented. So if you recall from last time, we had the following expression. If you have a linear map, if you have a linear map T taking this basis V1, V2, Vn to TV1, TV2, Tvn, let's say, yeah, so this expression that any n form acting on TV1, TV2, Tvn is same as determinant of T times alpha acting on V1, V2, Vn. So we are implicitly referring to this and we are making use of that at every point. Here the role of T is played by the Jacobian matrix of change of coordinates. Okay. So in this case, determinant stays positive at all points, and then you can see that if both charts are positively oriented, then you would have chosen the first case. You would have assigned this value, and that value remains unchanged because of the change of variable formula. Okay, the sign doesn't change. Okay, I'm not working out all the details. It is you have to apply the change of variable formula for this change of coordinates. Okay, important thing is the sign, because we know that under the change of coordinates formula, the integral is not going to change. So only thing that can change is possibly a sign. But we see that here the determinant, this is going to be an orientation preserving map, the change of coordinates. So therefore, integrals will have the same sign, and therefore we are done. Same thing happens if the second choice, if both the charts are negatively oriented. Okay. So the difference of sign comes from the determinant of this change of coordinates. Okay, so determinant of differential of the change of coordinates. In case 2, you assume that u comma phi and u tilde comma phi tilde are oriented in opposite way. So that means one of them is positively oriented and the other one is negatively oriented with respect to the specified orientation O on the manifold. So in that case, you would pick up, if you apply the definition using two different charts, you would get the difference in the sign. But then that gets accounted for in the change of variable formula by the sign of the determinant. Okay, so therefore, again in this case also, you will end up with the same quantity being defined as integral of omega on n. Okay. So therefore, this notion of integral of omega on m whenever omega is compactly supported and the support of omega lies within a single chart is independent of the chart. Okay. So now the next idea is to generalize this to the case when support of omega is not contained within a single chart. And the obvious trick here is to use partition of unity subordinate to a cover of the support of omega and define the integral and show that it is independent of the choices that we make. Okay, so let us go into it. So suppose you have a compactly supported n form on m comma o. Let ui be a finite cover of the support consisting of coordinate charts, and here you consider a partition of unity, a smooth partition of unity subordinate to this cover ui. We don't have to bother about what happens outside the support because integral of the out of omega outside the support, we will define it to be 0 for obvious reasons. So we'll focus on the region of support of omega, which is now covered by finitely many charts because omega is compactly supported. So on each of so if I look at this form psi I times omega, so you see that the support of psi I times omega is within the chart ui. Now once this happens, you are in the previous case, and therefore the integral of psi I times omega makes sense. You integrate this omega on this ui using the definition that we did, and take the summation over I, and you define that the resultant sum is the integral of omega on m. Okay, so again we are defining a notion that does should not the symbol suggests that we are integrating omega on m. So all the choices that we make should not change this right hand side. So that is what we'll do. So what are the choices that we made? We are choosing a finite cover of support of omega and also choosing a partition of unity subordinate to this cover. So let us assume that we have made two choices of let's say the other choice that we have is u j tilde and psi j tilde. So let us see why we get the same quantity on the right hand side. So and then therefore the definition will make sense. Now I would like to explain this idea geometrically what we are doing. It's not a trick that we are playing. See, in case of usual Euclidean case where we integrate a function, this is like saying that you are breaking the support into smaller sets, right? When we make use of partition of unity, we are breaking omega onto smaller sets, and then there we are considering the integration. This is the similar process of let's say subdividing an interval into certain smaller subintervals. And what we are saying is that if it does not matter the result of subdivision, the choice of subdivision does not matter. Okay, so in the case of Riemann integral, how did we do it? We said, okay, if you had partition P1 and partition P2, then we had something called as refinement of both partitions. Now we are following in the same spirit. What we are going to do is we are going to kind of refine this cover. Okay, so both this UI, the cover UI and cover UJ tilde, we are going to consider their refinement. But we don't have to explicitly refer to that refinement because this partition of unity does the trick. Okay, so with that geometric picture in my mind, let us then see what this. So let us focus on each of the individual terms. So psi I omega is an n form supported on UI. Now I am going to break it further because this UI will be covered by some of the UJ tildes, right? So this is your UI. For fix I, if I look at UJ tildes, these are UJ tildes. They are going to cover this UI, right? So I am going to focus on overlaps. In what way? In the following way. So the integral of psi I times omega can be written as sum of integrals psi j tilde times psi I omega. Okay, so if I focus on, yes, is there any question? I hear a noise because someone unmuted. Okay, looks like there is no question. So the form n form psi I omega, if I multiply it with psi j tilde, I am looking at if the form that is supported on UI, supported within this set UI intersection uj tilde. Okay, and you sum it over j. So this is very similar to refining a partition in case of Riemann integration. Now this left hand side, if you sum it over I, then you will get the following quantity. So the summation over I of integrals of psi I omega is equal to this double sum over indices ij of the n form psi j tilde times psi I times omega. Okay. Now you can do the same thing with the by replacing I with j. So what you do is you fix j. That means you are looking at a fixed uj tilde and cover it using ui's. Okay, and do the same trick. You will see that the integration. You will get this following quantity, that summation over j of psi j tilde omega is same as this double sum over j and I psi I times psi j tilde times omega. Now because these two quantities, so let me highlight them, these two terms are the same because this is kind of a common refinement on which you see the equality happening. So it says that the two integrals that get defined with the help of two different covers and partitions of unity, you get the same number in the end. So therefore, the notion of integration that we have defined is independent of the choices that we made. Okay. So I would like to remark here that whenever dimension of M is 0, that is M is just disjoint union of points, and when M is oriented, yesterday we saw that zero dimensional manifold, we can assign plus and minus sign at every point. So then what is the integration of f on M? So it is simply the sum of plus minus fp. Now you take plus fp if the point P is positively oriented, otherwise take minus fp. Okay, so now since we are taking f to be compactly supported, this sum is a finite sum. It's not going to be an infinite discrete sum. Okay. So with this understanding in dimension 0, we have the notion of integration defined for all manifolds. Okay. So let me take a pause and see if there are questions, comments, and suggestions you have.
Yeah, hello, Dheeraj.
Yes.
Uh, uh, yeah, the integration is one can do on measure space.
Yes.
I think people are familiar with maybe they have one course in measure theory.
Okay.
Yeah. Now uh, the spatial case of a measure is on a topological space, a Borel measure.
Hmm. Hmm.
Roughly a Borel measure, it assigns to every uh, open, relatively compact set
Yes.
some number. That number should be finite.
Yes.
That measure.
Yes.
Uh, yeah. So this is the idea of the Borel measure.
Yes.
Uh, Now, in the case of very special case of a topological space, a differentiable manifold using the differential structure,
Hmm.
if you have an uh, if you have an n form,
Yes.
then just the integral of that n form on
Yes.
an open relatively compact set
Yes.
that you are defining. So that is a
Sorry, I
Borel
couldn't.
measure.
Okay. Yes. Yes. But
That n form,
sir, I would like to just point out that for that, because we assign generally a non-zero number, a non-negative number to every open set or every Borel measurable set. Your form omega need not give you a positive number. For that, you will have to assume that the n form is positively oriented. Then yes. Otherwise, you get
yeah,
signed
yes,
measure.
yes, yeah, yeah. You take that setup, yes,
Yes. Yes.
yeah. So manifold is oriented, and you take this positive orientation, and you take this n form to be positively oriented.
Yes. Yes.
So the integral of omega on that open set,
Hmm.
which is relatively compact, that gives a positive number,
Yes.
and you can call that the area of that with respect to omega.
Yes. Yes. Yeah.
So that's a measure, and then we apply the standard measure theory
Hmm.
to define these integrals of functions.
Hmm. Hmm.
So this is bringing together
Hmm.
the topology, measure
Yes.
theory,
Yes.
and the differentiable structures.
Sure. Yes. Yes.
So the n form is really defines a you take this positive issue, positive negative issue.
Yes.
Then n
Yes.
form defines uh, a Borel measure.
Yes. Yes.
Yeah.
Yeah. Yeah. That is yeah, very interesting take, because yeah, it is very much we can see the connections from differential structure to measure theory. And also, interestingly, I mean, the one could see whether this measure, if I take a Borel measure, uh, one can ask the following question: when is it induced by some n form,
That
positively oriented n form?
this integral is on u.
Yeah. Okay.
Integral of omega on u, not on m.
Yeah. Yes. Hello. Am I still audible? Uh,
Yes, yes.
Yes.
Yes, sir. Yes, sir.
okay. Okay. See. Yes. Right. So Shall I proceed?
Yes, sir. Please go ahead.
Okay. Okay.
Sorry. Divergence of a vector field on a differential manifold with respect to an n form.
Yes.
So divergence, the idea is really that a vector field gives you a one parameter family of local diffeomorphisms,
Yes.
and then you are saying how a particular volume
Yes.
is translated by this one parameter group. And if you have
Yes.
the n form, then the derivative of that, of the sequence of numbers that you will get by integrating this n form on that U, that will be the divergence of that vector field.
On you.
Now,
Yeah.
at that point, finally, it's at that point. So the divergence does not mean the full Euclidean geometry or the Riemannian geometry. It only means an n form.
Yeah. Yeah.
With respect to that, you can define the divergence of a vector field.
Yeah. Yes. Yeah. Yeah. Thank you for interesting and insightful comments. Okay. So in general, if you have a submanifold of dimension k, and let's say that if you have a co-oriented submanifold of dimension k of this manifold M, then you can integrate k form on S in the following way. So let us say that omega is a k form on M such that its restriction to S is a compactly supported form. So how do we take restrictions? It's really you look at the inclusion map from S into M and define the symbol that is the integral of omega on the submanifold as the integral of the pullback form via this inclusion map. So we can make sense of integrating k forms on k dimensional submanifolds of your ambient manifold M. To make sense of this notion, we have to have oriented k-dimensional submanifolds, and the form should restrict to a. So why did I say this? Because in general, yeah. So I would like to talk about integrate. I want to go towards the Stokes theorem, in which we are talking about integrating a form defined on M, n-1 form on M, onto the boundary. So, yeah, I am discussing that in the next point. So, if M is a compact oriented n manifold and omega is an n-1 form on M, then we can define its integral on the boundary. The definition is given by, first you pull back the n-1 form onto the boundary and integrate it out. Because M was compact, its boundary is also a compact manifold and it gets an induced orientation from M. So we have everything in place, so we can make sense of this integral of pullback form on boundary of M. Okay, so this is essential to go towards the Stokes theorem. Okay, so before I go towards the Stokes theorem, I first of all quote few properties of the integrals that we have, the notion of integrals that we have defined. One is obviously the linearity. So if you take two real numbers A and B in R, and let's say omega and eta are n forms or on M is oriented, we can assume that omega and eta are compactly supported so that everything goes through. So in that case, integral of A times omega plus B times eta is, so this integration distributes over scalar multiplication and addition, the linearity property. Now since M is oriented, we can do the following thing. We can assign M the opposite orientation, okay, and we'll denote the corresponding manifold by this symbol minus times M. So then integral of omega on minus M is, you can see that this is the same as integral of omega on M. How do you see that this immediately? Because the identity map from M to M is a diffeomorphism, but with the orientations that we have given. So let us say identity map from M to minus M. So this becomes an orientation reversing map, and therefore you pick up this minus sign. Yeah, so another thing to note is that if omega is positively oriented n form, that means recall the definition that at every point, if you have a positively oriented basis, then omega evaluates to on that ordered basis to give you a positive number. This is how we define positively oriented form. So if you integrate positively oriented form, then you will get a positive number. This is something, a generalization of the following thing in the Riemann integral, right? If f is a positively valued function, then integral f is also greater than 0, right? So we are going parallel to the notion of the properties of integrals in Euclidean cases. So yeah, so if you have an orientation preserving diffeomorphisms, then the integration, the integral is independent of the change of coordinates. Okay, that is something that we have seen, but I have just quoted the global version. And whenever f is orientation reversing, integral changes the sign. Okay, so now yeah, we are ready to go into Stokes theorem. I would like to take a pause and see if there are comments, questions, suggestions at this stage.
The name of that person, Stoke or Stokes?
Yeah, so this is this is apostrophe x. So Stoke.
No, I think the original name was Stokes.
I see. Okay. Okay. So
Stokes
I stand correct. Yeah, I stand corrected then. So should I write it in this way? Yeah, but yeah, I again checked the spelling. It is written as this way. So Stokes theorem. So whether this is apostrophe s or the person's yeah. Okay. So let me start. Just give me a moment. Yeah. Yeah. The setup is that you have an oriented smooth n manifold with boundary, and let omega be a compactly supported smooth n minus 1 form on M, then the integral of d omega on M, d omega is a n form. This equals the integral of omega on boundary of M. So we understand both the sides. We have seen that the right hand side does make sense because boundary admits an induced orientation, and when we say we are integrating omega on it, we are simply pulling back the form omega on defined on M using the inclusion map. Okay, so this statement requires some remark because I did not so this has a special interpretation when boundary of M is empty. So that means you're looking at a closed manifold. Okay, then the RHS is to be interpreted as 0 because the boundary is empty, so the integral on that side is 0.
Sir, if boundary is empty, you mean the manifold without boundary, right?
Yes.
I
So
think you
it's
said
called,
the closed manifold.
yes, closed means, okay, in topology, closed means compact without boundary. Okay, this is a terminology that gets used. Okay, so,
But boundary being empty doesn't mean it has to be compact, right?
yes.
Uh,
Yeah, you're right. Yeah, you have a point. If I am talking about open manifolds, so it need not have a
yeah,
boundary.
but
Even in
but
that
I
case, this is true. My
but
statement was not correct. I shouldn't say closed manifold. It's just that whenever the boundary is empty, we have to interpret the right hand side as 0.
but I think you might be still true, still saying the right thing because
No. My
omega
statement.
is compactly supported, right? So instead of
Yes.
looking at complete M, you can look at a uh, subspace of M.
So for instance, take Rn. Take the usual case of Rn. So it does not have a boundary, right? So, and let's say I have omega compactly supported. So which means, okay, actually you brought up an interesting point. Let me explain. So if I integrate this M over, sorry, Rn, then you can see that it is good enough to integrate this form d omega onto some large cube, right? Because omega is compactly supported, we can take a let's say a cube of side length capital R such that R is such that the support is inside this cube, and then you actually integrate it out. You will see that you have to integrate the you will end up with values of omega on the boundary of this cube, but you know that the boundary lies outside the support, so values of omega are going to be 0 on the boundary of that cube. Okay, so in dimension 3 I would have drawn a cube. Okay, so in that case so if I just drop that it is without boundary, then it is not necessarily a closed manifold. This is the counter example. So what I was saying was strictly incorrect statement. So thanks for your pointing it out. Okay, but yeah, so you saw in fact how this Stokes theorem is going to work in a general manifold case. If you understand the case in Rn, why So this statement means just that if you have a compactly supported function and if you integrate it out, the derivative of that function, right? So its integral will be 0, because you have to just take the difference of values of f on various sides if you start integrating. So this integral, in your usual sense, it will be from, let's say, minus r to r, minus r to r, and yeah, df dx1, dx2, dxn. And you can show that after integrating it out, I apply this fundamental theorem of calculus for every variable, and you see that you have to just look at the values of the function on the sides of this cube. Take their differences as you start integrating it out with respect to the variables, one at a time. Okay. Hello, am I audible? Looks
Yes.
okay. Yeah, somebody raised a hand. Please go ahead with your
Then
question.
is the diffeomorphism is orientation preserving? Like in this case,
Which diffeomorphism are you referring to?
no, when uh, when I take the boundary and uh, we if we orientation is done, তাহলে
I
then
think Dheeraj, you should make the
Yes.
statement of Stokes theorem for M a
Uh,
compact orientable manifold with boundary.
Sorry, sir, I could not hear you. Could you please repeat?
You should make the statement of Stokes theorem for a manifold with boundary. And yes, compact, so you get finite numbers. So for a compact manifold M with boundary dm, the integral
Okay.
of
Yes.
so the
Okay.
LM is oriented smooth manifold. তাহলে this orientation is preserved. M is the smooth oriented smooth manifold
Yes.
with boundary. তাহলে if this orientation is preserved in the manifold.
No, your statement doesn't make sense. When you say it is preserved in the manifold, what do you mean by it? So you can talk about orientation preserving diffeomorphism or orientation reversing diffeomorphism. So you have to set up then a diffeomorphism between M to some other manifold and then talk about its preservation, right? So
Okay.
what was your question? I didn't quite follow. And yeah, so coming to Professor Kulkarni's comment, so yeah, the statement I can rewrite it as, because I am dealing with compactly supported form, I am writing this statement. I am not assuming that manifold is compact, but for compact manifolds, we will have the following statement. So restatement. So for M, for compact case. So let M be a compact N manifold with boundary del m, and then rest of the statement is as before. Let omega be n minus 1 form on, oh, okay, I still compact oriented, this was this on M, we have integral of d omega on M is equal to integral of omega on boundary of M. Yeah. So, and what I was saying earlier, that for closed manifolds, so that means the boundary M is empty. This right hand side is to be interpreted as 0. The integration on empty manifold is to be interpreted as 0. Okay. So, yeah, right. So, is there any question with regard to the statement of the theorem? Okay, looks like there is no question. So, I've got roughly 15 minutes. So, I will proceed. Maybe, yeah. Let me first tell you how to recover the fundamental theorem of calculus and fundamental theorem of line integrals. It's already built in the statement. Okay, so let us write it as corollary. So suppose M is equal to, just a moment, I think I forgot to mention in the remarks what happens in the dimension 1 case. So dimension 1 case, the statement, the right hand side of the statement is an integral over 0-dimensional manifold, and we saw that integration on 0-dimensional manifold is to be interpreted as sum. Okay, with that, we see that if you take a compact interval in R, M to be a compact interval in R, then so I will integrate for any smooth function f. Smooth function f means that it is a restriction of a smooth function on some larger neighborhood containing this AB. What we see is the following. So integral, if I apply Stokes theorem, then I should get the following statement. Integral of df on AB is same as integral on the boundary. So boundary of AB, which I am writing right now in this form, of f. Right. So let us look at the right hand side carefully. So what is the boundary? Boundary is union of 2 points A and B, but the orientation induced at B is positive. And at point A, the orientation induced, because we are using the orientation given by the standard orientation on this interval, which goes from left to right. So this is positive and this is negative. We saw it yesterday. So here it will be sum of two quantities, sine sum of two quantities. And this coincides with our fundamental theorem of calculus. Okay, so let us also see how it gives us fundamental theorem of line integrals. It is along the similar lines. So for that you will need a smooth embedding. So suppose this is corollary 2. Let gamma be a smooth embedding of this interval into some manifold M, but you could have taken M to be R. So I will state it in generality. Be a smooth embedding then you have an embedded submanifold, the image of gamma. Then image of gamma is one-dimensional submanifold of M, and we give we can induce an orientation on this submanifold by simply transferring the orientation on this interval AB. Right? We can push it forward via this embedding map gamma, which is oriented by pushing forward the orientation on the interval a comma b. Then we can for any smooth function f in C infinity m, I want to integrate this df on this image gamma. Then we saw that by Stokes theorem we get this is same as the integration of f on the boundary of image gamma, which is simply f acting on gamma at b minus f acting on gamma at a. So this is a generalization of what we saw in example 1. You can similarly obtain, so you can obtain also the Green's theorem, so corollary. Green's theorem. So suppose, so let us do it for the disk. So let p dx, so p y dx plus q x y dy be a one form, a smooth one form on the unit disk D2 inside R2. Okay. Then we have, by Stokes theorem, if what I will get, the integral on D2 of D of this one form is same as integral of this form on the boundary of this disk. So which is a familiar statement. You can work this D expression out and you will get that this is simply dq y, the partial of q with respect to y minus partial of p with respect to x, dx wedge dy. So you integrate this form out, that integral is same as the line integral p dx plus q dy. Yeah. So the list is you can in the similar fashion you can derive the Gauss's divergence theorem and so on by taking appropriate forms. So it's an interesting and not so hard exercise to uh, guess those forms and get the various theorems that we had quoted in the lecture 1. Okay. Let me also, is there
It's
any
q,
comment? Uh,
it's q sub x minus p sub y.
Right. The coefficient of dy should get, sorry. Yeah, thank you for, yes. Yeah. So, yeah, there is one more interesting corollary is the following. So, we can show that on S1, so corollary, this is an interesting corollary from the following viewpoint. Corollary, the form, one form d theta on S1. Okay, think of S1 as the unit circle in R2, and you have this one form d theta coming out of the coordinate system for the polar coordinate system, right? So d theta on S1 cannot be exact. Okay, how do we prove this? It's a very nice simple proof. So suppose it is exact. Suppose d theta is equal to some df for some f in C infinity, that is smooth function on S1. Then by Stokes theorem, what do we have? The integral of df, that is integral of df on S1 is same as the integral of f on boundary of S1. Okay, so which means as we saw before, this RHS is 0, right? So this would imply that the integral of d theta on S1 is 0. But this is a contradiction because you know that d theta integrates out on S1 to give you 2 pi. So this is a contradiction. To the fact that okay, so right, so I have explained you the interesting directions in which Stokes theorem can be applied, and you can recover all the theorems. The proof of it, let me quickly hint at the idea. You can also work out the proof by yourself, because the way we have defined integrals, we first defined it locally and then use partitions of unity to define the integration uh, on the entirety of the manifold. Okay, so let us discuss the idea of the proof of Stokes theorem. Of the proof. So we can take the similar plan for this proof. We can try to prove this theorem first of all locally. Okay, so we will take a compactly supported form. Take omega, a compactly supported n minus form on Rn. I think this case I was discussing as one of you pointed out, the case of open manifold. So when we integrate out d omega on Rn, we can write, we know that because omega is compactly supported, there is some large cube such that the support of omega is within that large cube. So this is same as integration on minus r to r, this interval, and take n-fold Cartesian product of it and integrate it out. The reason is that because omega is compactly supported, therefore d omega also becomes compactly supported. So in particular, if support of omega is within this cube, large cube, then the support of d omega will also lie within the same large cube. So therefore, the integral outside that will be 0 because d omega is 0. Yes. Hello. Yes. Is there any question? Okay, it's just some noise, I guess. Is there any question? Somebody has unmuted and I thought there was a question here. Okay, so if you work this out in the usual integrals, so you will have n-fold integral from minus r to r, and you work out the expression of d omega. So in the local coordinates, it will contain partial derivatives of coordinate of coefficient functions. So omega will be summation of, let's say, small omega, small wi, and dx1 wedge dx2. The dimension of the space of one forms, n minus 1 forms at any point is this is n dimensional space, right? So we can make use of interesting notation over here. So the basis will be given by simply deleting some dxi. So in many times you apply hat on that in order to say that this term is deleted. Okay. And this sum is over I. So you have such a form. You take d of that form, it will be summation I over j. I'll directly write down the expression. So d omega partial of omega I with respect to xj dx1 wedge dx2. Okay. So this remains as it is. Yeah, so you differentiate this n minus 1 thing as it is, and you express it j. Now you can put it in. So basically, you again get n form together with some sign. Okay, so this will be equal to. Let me write down the final form. I ranging from 1 to n minus 1 to the power I minus 1. So those many transpositions you require to put this xj into the position, ith position. Okay, so this term is not, this sign is not mysterious. It is something that comes out of, and then you take the usual. So this is the form that you are integrating on the cube. Now you see that the partials of Wi are also compactly supported. So when you start integrating it with respect to each variable, you will see that the terms will vanish. All the terms will vanish.
It should be the derivative of omega I with respect to xi.
No, here I was using I for the components of that vector. So this Wi is a component in the direction of this basis vector for n minus 1 forms,
Right.
where I am deleting, and then when I differentiate it, I take its partial with respect to xj, and then I have the corresponding xj term.
Here.
Now,
Next term.
the next line.
Yes.
Right. Yeah. So this terms, the only surviving term is, yeah, partial with respect to xi. Yes. Yeah, you are absolutely right. Yes. So now it's a question of integrating out each of the term, and you know that each of the term, if you integrate it out on the cube, you will see that you will get 0. So this part is easy. So let us assume that we are now working on upper half space. So that means we are considering the case near the boundary. So okay, I'll just take 2 minutes to explain this part and leave it at that. Okay, so case 2, assume that M is equal to upper half space. Okay, so now in this case, again, because omega is compactly supported, we are going to consider the following rectangle. So let us consider the rectangle or the cube C of the following type. So I will take minus r to r, a cube of size dimension n minus 1 cross, because this last coordinate is a coordinate where you're allowed only to go to the non-negative direction. Okay, so that, right. So roughly the picture is something like this. So you have, this is r n minus 1, and this is the direction, and the support of omega is something like this, and the cube that we are looking at is here. Okay. Now again, if we perform the same, yeah, so this computation will be useful even in the case of Hn. We will see that the integration of d omega on Hn will be, you have to take this sum over I minus 1 to the power I minus 1 integral over this C of individual term. So partial of Wi with respect to xi, and yeah, you have this form to dxn. Now this is an alternating sum. When you look at the term I is not equal to n. Okay, so if I'm looking at the terms when I is not equal to n, what is happening? By the earlier argument, all those terms will vanish. Okay. So the only term that will remain is the following. It is the term, the I equal to n term. So that is the term minus 1 to the power n minus 1 integral over okay, now let's expand this integral. So it will be minus r to r minus r to r, and you have this we are integrating it out with respect to nth spot. So I have omega n of x, and I have to apply the limits from the last coordinate equal to 0 to last coordinate equal to r, right? And rest of the variables are kept untouched. The dx1 which up to dx minus 2. Okay. I mean, for the other terms also you will get something similar, but you know that omega i's are compactly supported and they will vanish. So all the remaining terms will vanish. So this is the only term of interest. So this is the same as yeah, you can now compensate for this. You can, so if you evaluate this inside, then what will happen? Only one of the term will survive. If I plug in the last coordinate equal to r, that term will also will be 0 because omega is supported within this cube. So the only term that survives here is minus of omega n evaluated at xn equal to 0. So that minus sign I'll combine it here, and outside I'll write minus 1 to the power n and this is the term omega n at evaluated at the portion of the boundary of this upper half space it is evaluated on the boundary of the upper half space, and you get this term. Okay, so now if you work out the term omega acting on boundary of Hn, it will coincide with this term. Okay, so this is just a computation. Okay. Main thing was here we see that only in the coordinate, the last coordinate, the term survives. Rest of the coordinates, the terms are 0. Now this is the case when you take upper half space, and the general case you can again perform by taking this partition of unity, making things compactly supported and bringing it to either of the cases, case 1 or 2, okay, and tracking the terms down. Okay, so I think I'll stop here. I have already overshot by almost 15 minutes. So thank you for your attention, and yeah, thanks a lot. I think that this ends my series of talks.
Sir, I have some questions.
Please go ahead.
Okay. Just a little bit earlier, whenever a function f from closed interval ab to some manifold has a dimension 1, that portion can you show? Just little bit earlier.
So what f is smooth?
A smooth manifold, then f is of dimension 1. Okay. Just little bit earlier. If you go back to that page.
Okay. Okay, you're talking about the generalization of yeah.
Yes,
This is
yes,
the
yes,
corollary
yes,
to.
yes.
Okay, okay.
Yes, yes, both embedding.
Embedding.
Embedding, smooth embedding.
Yes.
Image of R is one dimensional manifold of M. Okay,
Yes.
here is there any role of the closed interval AB? Instead of closed interval AB, if we take any rectangle, square, or cube, can you say
Yes. Yes.
about the dimension of image R? That is the
So yes, you can say that dimension of the domain gets preserved because you are assuming you are working with a smooth embedding.
yes,
This I don't know whether this term embedding has been defined.
exactly.
Okay, embedding means first of all, it's a one-to-one map.
One-to-one, it is
It,
homeomorphic or diffeomorphic to some subspace.
yes, and not only that, the derivative map is injective at the level
Mm.
of tangent space.
Yes.
So it's an uh, immersion. Embedding
Yes.
in particular is an immersion.
Masha, right.
Yeah.
Someone, Bijita বিশ্বাস has raised her hand for a long time.
Okay. Okay. Sorry. Because as I write, I
Okay,
am not
okay.
able to type.
Okay.
Please go ahead with the question. The
Hello,
person who has raised the hand. Yes.
Vijita, have you any question? Vijita Biswas.
Oh, no,
no,
sir. Thank you. Sir, one more thing I would like to know. Actually, whenever, just before, if you go before,
Yeah.
that is,
Okay.
that's I don't recall. Whenever that is just before
Yeah.
Stokes theorem.
Shall I go even before?
Okay, just wait, sir. Okay, for one dimension, that is, you have used one term. Actually, just before. Okay.
Yeah. So I think I was talking about this when dimension m is 0.
Yeah, exactly.
What is the meaning of integration on zero-dimensional manifold?
Exactly. Now, just whenever the dimension of one, and you have used some term, the term or something like that.
Okay. Yeah. Right. So yeah. So when I interpret Stokes theorem in when the dimension of m is equal to 1, what I'm going to do is take a zero form on m. Right?
Yes.
I have to take n minus 1 form. When n is equal to 1, I will be taking zero form.
Zero form.
But what is zero form? Our convention is they are smooth functions, right?
Yes. What function, sir?
Smooth functions.
A smooth function. Okay, sir.
So in that case, I will be, if I interpret the statement of Stokes theorem, I will have to take the df and integrate it out on m. That is same as integrating out f on boundary of m.
Okay.
But m is one dimensional, so the boundary of m is zero dimensional manifold.
Exactly.
So that means that this integral on the right hand side is sum of values of f at various points. This is a signed sum, plus minus.
Okay. There is a singleton set points.
Yes.
Yes.
Yeah, exactly. These are discrete points.
Okay.
Yeah.
Okay, thanks, sir.
Yeah. Thank you. Hello. Yes, sir.
Okay, sir. I think,
Okay, thank you.
So thank you very much for giving us time.
Yeah.
Sir, please share the lecture.
I will share. Yeah, I think yesterday also the
It will
notes
be
are
shared,
still
madam.
remaining.
It will be shared. Whenever
Yeah.
sir sends, it will be shared.
Yeah,
What
I
the
will
reference
immediately.
was? Sir, reference.
Yeah. Reference is I like this book by John M. Lee, Introduction to Manifolds.
Yes.
Okay, so it is Yeah, I have noted it in the notes. So
Yes.
you will also,
Yes.
yeah. There is another book, Differential uh, Analysis on Manifolds and Lie groups. So that is by
Cumulative.
Frank Warner.
Oh,
It's about
that was your foundations of differential geometry.
Foundations of Differential.
foundations.
Yeah, both the text I have written it down in the notes. You will have it in the,
Yes.
yeah, yeah.
So, thank you,
Okay,
sir.
thank you.
सर अब हमने
Thanks a
आपको
lot for.
देखा ही नहीं.
Oh,
So,
okay.
you
Yeah,
can
yeah.
सर वो
The
send me
reason.
कैमरा
video.
अरे बाप रे.
So, sir,
So
I
the thing is, it doesn't support that much of bandwidth. If I keep the video on and keep writing, then it doesn't really. So the connection becomes poor. So yeah,
and
Okay, sir.
because you have such those topics which are generally not being taught in universities.
that's true.
Basically,
That's true. Yeah.
that basically on integration on manifolds, these are very rare in university
Hmm.
courses.
Yes.
Yes. Yes. And also,
Generally,
I just wanted to say that, of course, the ambition, the syllabus set for lectures, yeah,
yes.
was very high. So I was initially
Very high.
puzzled. How can I achieve? See, I could not cover Sar's theorem. I would have
Sounds
liked to talk.
exactly.
Yes. So I would have liked to talk about it, but within 4 lectures, I knew from the beginning that it would be a Herculean task and relate it with the knowledge that already we have. It takes some time. Typically,
Yes, sir.
we take half a semester to cover the
Yes,
topics
sir.
that were assigned to me. So I was telling
Most
this to Professor Gauri Shankar, but I hope that despite not achieving our target, whatever we did, I hope it has been something is coming out of it. I hope your
yes, sir.
understanding is enriched in some way.
It was so
So,
good,
Yeah.
sir,
sir.
it was very nice.
Okay, okay. Thanks a
So,
lot for your nice lecture.
formally, I thank from
Thank
on
you.
behalf
Thank
of
you.
on the organizing team for
Thank
accepting
you.
our invitation and to be part of this summer school. And your lectures were very excellent. I was very much. I can say that I was very much involved in your lectures throughout
Thank you.
these 4 lectures.
Thank you.
So,
Thank you. I take it as a very positive thing because just on a lighter vein, I know it is very difficult to attend lectures at 2 o'clock, right after lunch.
yeah.
Because I myself struggle to keep awake during that time. So I know what audience, if I really, if I manage to keep you awake, that is also something.
Yes.
Yeah.
Thank you, sir.
Thank you, sir. Thank
Thank
you.
you. Thank you. Thank you. See you sometime.
Okay, okay, bye.
Okay. Bye.
So please be connected. Almost we are having 5 minutes for tutorial session. So I request participants to be connected.